This is Jack Creel, and I'm going to be explaining my problem set for topics 5 through 12. So the first question is going to address topics 5 and 7, and it states that you recently decided to collect and filter your own water supply from a nearby river. So you have a pipe with the dimensions of 10 centimeter radius and a length of 12 meters, and water is flowing through it at 30 gallons per minute from the river. And then at the end of the pipe, you have a filter that's 25 centimeters long with a void fraction of 0.3 and a particle diameter of 3 millimeters. It wants you to determine the Reynolds number and friction loss through the pipe, the friction loss through the filter, and how the friction loss through the pipe would change if the exact same flow was laminar. So to start, we draw a diagram and list our assumptions. We're assuming water is incompressible with constant viscosity and density, and it's a Newtonian fluid. So those are pretty basic assumptions for water, and that the temperature is 20 degrees Celsius. So first we calculate the linear velocity based on the volumetric flow rate in the area. And we then use that linear velocity to calculate the Reynolds number, which once it's calculated will tell us that this flow is indeed turbulent. So we're going to use the turbulent version of the friction loss equation. The only thing that we really need in here is the friction factor, which is calculated as followed based on the Reynolds number. Plug everything in and find that the friction loss through the pipe is going to be 3.36 times 10 to the negative third joules per kilogram. Moving on to the friction loss through the filter, we calculate the superficial velocity in the same way based on the volumetric flow rate. And now we're going to use the ergon equation to find the friction loss, since this filter is porous media. And we know that this equation can indiscriminately be applied to both laminar and turbulent flow, so we don't have to worry about that. And we'll find that 18.3 joules per kilogram are lost to friction in the filter, which is much more significant than friction losses in the pipe, as is to be expected. Now, finally, if the same flow was laminar, we would instead use the laminar version of the friction loss equation, and we would find that the friction loss is slightly less. It is 5.81 times 10 to the negative fourth joules per kilogram. So it's important to note that friction will be slightly less for laminar flow than turbulent, even at the exact same conditions. Question 2 is going to address topic 6 and 8, and it states that the filtered water from the previous question is now going to be drained into a collection drum open to the atmosphere to be stored and pumped out as needed for drinking water. So the first part tells us that the pump you plan to assemble 0.5 meters above the drum, and you're going to have the water enter at 0.2 meters per second. The pipe has one 90-degree bend, and it wants you to find the maximum net positive section head that your pump could specify given these conditions, and the temperature is 20 degrees Celsius. So that really means you're going to calculate the available net positive section head of the fluid, and then say that that is the maximum a pump could specify, even though you're going to want to go lower. The second part tells us that the drum is in your yard, and when it's especially windy, you start to worry that the wind might tip it over. So it's a spherical drum with a radius of 2, and on a really windy day when the wind speed is 12 meters per second and the temperature is 5 degrees Celsius, you want to find the drag force being exerted on the tank by the wind. So first, again, we start with diagram and assumptions. We're setting our coordinate system so that z is 0, that the height is 0 at 0.1 here at the fluid at the top of the tank. We're assuming we're at sea level, so the ambient pressure is 101 kilopascals. We're assuming that the velocity here at 0.1 is negligible compared to the rushing fluid through the pipe. We're assuming that both the tank and the pipe are relatively smooth, so we're not going to worry about the friction loss due to just the roughness. Shouldn't be very significant. And then we're going to say that the water level in the tank is going to be constant, so the inlet and outlet streams are the same, and the elevation at 0.1 will not change. And then we're also assuming that there's no work done by the fluid or on the fluid, and that we're going to ignore the exit losses because we're really talking about the available net positive suction head before it enters the pump here. So first we're applying the Bernoulli equation from points 1 to 2. We know that the velocity at 0.1 is negligible, that our coordinate system says that the height is 0 at 0.1, and that there is no work terms. So we can rearrange this equation for the pressure at 0.2, and the only thing we really need in here is going to be the total head loss, which is going to be caused just by the entrance and the bend, as it seems. So we go into our handouts and we can find the loss coefficient for both this entrance and this bend, and then we will use those, which multiplying by velocity squared is going to give us the total head loss, so they both contribute to the total head loss in there. And once we have the total head loss, we can calculate the pressure of 0.2, and then we will be able to use that to plug in here and find the net positive suction head available by the fluid. So we plug everything in. We also have the saturated pressure of water from the handouts listed up here. And we find that the available net positive suction head of the fluid is 9.61. So that's going to be your absolute maximum for required. You're going to want to go lower than that. And then the second part, we're finding the drag force now, which can be calculated based on this equation. So the main thing we need here is going to be the drag coefficient for this fluid stream. We know that the drag coefficient is based on the type of flow, so based on the Reynolds number. So that'll be our first step. And we find that the Reynolds number is extremely large, which means this flow is very turbulent, which is to be expected since it's flow over a really large object, the tank, and it's very fast flow. So when we go into figure 6.24 in our handouts, we know that after a Reynolds number of about 1 million, so once flow is extremely turbulent, then the drag coefficient will remain approximately constant at 0.15. So since this is such turbulent flow, that's going to be the drag coefficient we're going to use. And we will find that the drag force exerted on the tank by the wind is 172.27 newtons. The third question is going to address topic 9, and it's talking about a rocket engine that produces combustion gases, mostly carbon dioxide, and it propels it through a converging diverging nozzle. So in the chamber before the nozzle, the temperature is 800 degrees Celsius, the pressure is 1 megapascal, and the velocity of the gas is negligible. So for the first part, it wants us to find the pressure and temperature at the throat of the nozzle in order for this flow to choke. And the second part says that if it's exiting to ambient pressure, 101 kilopascals, what is going to be the exit velocity and exit Mach number of the gas. So we start with our diagram again and our assumptions. And so we're not as much assuming as we are told that the velocity at the nozzle inlet is negligible. So that means that the inlet temperature and pressure will be equal to the stagnation temperature and pressure since the gas is stagnant. We're assuming that there's no work. We're assuming that the fluid is incompressible, that the change in potential energy is negligible as it should be. And then although this is mostly carbon dioxide, we're going to analyze the system as if all the gas is carbon dioxide. We're saying that the flow is one-dimensional, it's isentropic, we're at steady state, and we're going to treat carbon dioxide as an ideal gas. So for the first part, we need to calculate the critical properties of this flow. So in order for it to reach sonic velocity at the throat, it needs to reach the critical properties at the throat. So they can be calculated as follows. So we know that it needs to reach a value of almost 700 degrees Celsius and about 548 kilopascals at the throat in order for it to be at sonic velocity there. So next, to find the velocity at exit, first we need to find what the exit temperature is. So based on the pressures and temperature, we can find that. And then once we know what the temperature is going to be at exit, we can do an energy balance on our entire system here. So we know it's steady state, nothing is changing with time. We know that the velocity at inlet is negligible, and we know that the potential energy change is negligible. So then we can rearrange that equation for the exit velocity, and we know that for an ideal gas, the enthalpy change is going to be equal to the temperature change times the heat capacity. So we can sub that in there and then calculate the exit velocity and find that it'll be 735.5 meters per second. And then we need to find the local speed of sound, which can be calculated with this equation. And then the Mach number is essentially just the ratio of our velocity to the local speed of sound. So we find that at exit, the Mach number is 1.7, which means that the fluid is traveling at 1.7 times the local speed of sound. So problem 4 is going to address topics 10, 11, and 12, and it states that you're just trying out skimboarding and begin to think of the fluid mechanics phenomena that are at play here. So imagine you run and jump onto a large flat surfboard and glide across that very shallow water, only 5 centimeters deep at 4.2 meters per second. So we want to derive an expression for the velocity profile for the water between our surfboard and the ground here, assuming that the water's temperature is 20 degrees Celsius. And we're going to find this expression both analytically and numerically. So here's our diagram with an initial guess at our velocity profile. And we're going to assume that there's no slip at either of the solid boundaries between the fluid. So that means that the fluid will be moving at the velocity of the solid it's in contact with at both interfaces. So we're assuming this is steady state and fully developed flow, that all of the velocity is in the x direction as defined by our coordinate system. There is no velocity in either the y or z direction, which should be accurate. We were told that this is a very wide system relative to the very small depth here. So that will mean that there is no z dependence in any way. We're going to assume that water's density and viscosity is constant and that it's Newtonian as usual. We're assuming there's no pressure gradient. It's open to ambient at both sides, so that should be accurate. We're assuming that this ground is fully horizontal, so there's not going to be any gravity dependence. And so we're going to start with our microscopic continuity equation. It's steady state, so nothing's changing with time, and we have no velocity in either the y or z direction. Rearrange that and find that the velocity in the x direction is not changing with x distance. So then we move on to our microscopic momentum balance, steady state, nothing's changing with time. Directly from our continuity equation, we know that this first order derivative is 0. Again, there's no velocity in y or z. There's no pressure gradient. There's no gravity dependence since we're fully horizontal. And from our continuity equation, if this first order derivative is 0, then so must be its second order derivative. And we were told it's very wide, remember, so that there's no z dependence in any sort of way. And all that leaves us with is this second order derivative, and that, once we rearrange, we will find is equal to 0. We can integrate that twice and find an expression for our velocity in the x direction in terms of these integration constants. So we need to solve for those constants using our boundary conditions, which are listed up here. They're both based on the no-slip condition. So that means that the fluid will be moving at the velocity of the solid it's in contact with at both sides. So that'll be 0 at the beach, and the velocity of the surfboard, 4.2 meters per second at the top boundary. So we can solve this fairly simple equation for both of those integration constants and find an expression for our velocity in the x based on distance in the y. Here it is in terms of variables, and there it is numerically. And then to find this same expression numerically instead of analytically as we just have is fairly simple. We know that this second order derivative is equal to 0, and finite differencing tells us that the second order derivative will be equal to this expression. And so after we rearrange that, we can find an expression for the velocity in the x direction at any node based on the velocity in the x direction at the nodes around it. So we can do that. That's done here in an Excel. And these values are pretty much the exact same. The only difference is since this is done iteratively, the decimals are very long. But once we plug all that in and graph it, we can see that our guess at the velocity profile was very accurate and that it's changing linearly from 0 to the velocity of the surfboard here.